PhD degree from Department of ECE, NIT Kurukshetra, India. His current research interests include modeling of the semiconductor devices and circuit co-design issues. He has published several number of publications in various indexed journals. He was the sub-reviewer of third International Conference on VLSI Communication and Signal Processing, VCAS 2020, and International Conference on Advances in Computing, Communication and Security, I3CS 2021. Thanks, sir, for accepting our invitation to be a resource person. Now I request Dr. Shikar Gupta to take over the today's session on spatial technology in MOS devices.
I request you, sir, to please convene the session. Over to you, sir.
Thank you, Dr. Gautam. Good evening,
Thank you.
everyone. Am I audible? Please let me know.
Yes, sir, your voice is audible. Yeah, your screen is visible, sir. You can proceed.
Thank you, Dr. Gautam, for the brief introduction. Firstly, I would like to thank Professor Reddy, Dr. Vijaya, and Dr. Tyal for inviting me as a resource person for the online activity on next generation material and devices at ERSA University Warranty. I welcome all the participants and third session, day 2 of this activity. So I'm going to start on the spacer technology in MOSFET devices. Firstly, we have a brief introduction of the advanced MOS devices. Later, we will discuss about the source drain underlap MOS devices and fringe capacitance in the underlap region. Also, after that, we are going to discuss spacer dielectric in the underlap region. Finally, we are going to discuss the spacer technology in the underlap region of the MOS families. J. Atla at Bell Laboratories introduced the FinFET devices, and later in the 80s, when the CMOS technology took over the semiconductor industry, Gordon Moore reported that in every 15 to 18 months, the size of the transistor on IC is almost double. So this leads to the aggressive scaling of the MOS devices, leading to an advancement of short channel trap in the form of subthreshold DIBL of current leakage and various others. To mitigate these effects, we have introduced multi-gate, multi-dimension MOS devices, which are basically under the category of the advanced MOS devices. So basically, we have SY devices, then we progress to the double gate devices, then we progress to the double gate FinFET devices, tri-gate FinFET devices, gate all-around nanowire devices. So there is a need to mitigate the parasitic capacitance in the multi-gate devices. Since the advanced MOS devices like TG MOSFET, FinFET has very good electrostatic integrity, but they also have high series parasitic capacitance from the source drain region. To minimize these effects, source drain extension doping profile has been introduced with the optimized value of the underlap lamp. Also, in the multi-gate devices, we have seen that there are very parasitic capacitance which dominate the overall capacitance of the devices. These parasitics are totally undesirable and can be neglected using various techniques. One of these techniques are introducing the source drain underlap. To overcome the uh, to overcome this problem, gate underlap is introduced for reducing the parasitic capacitance, as I discussed. As we optimize the underlap length, we significantly reduces the fringe capacitance, resulting in the enhanced device performance for low power dissipation. Optimized value of the underlap length enhances the on current, drive current, and counter the series effect, series resistance effect, short channel effect, and gate range induced barrel loading effect. These devices enhance the circuit distortion and the emission power of the device when compared with the conventional. Underlap device shows significant improvement on short channel effect, self-repeating effect, reduces the parasitic capacitance and resistances, series resistances, which enhance the low power performance for low power circuit application when compared to the conventional MOS family devices. Incorporating the anal underlap in closed-end underlap, especially the closed-end underlap, the device became appropriate for the thermally adequate low-power nanoscale mixing circuits. The fringe capacitance in the underlap devices. Parasitic capacitance, as we already discussed, are the major factor for the performance of the advanced MOS family devices. So, the, one of the major parasitic capacitance is the overlap capacitance, outer fringe capacitance, and inner fringe capacitance. But as we introduce the underlap in the MOS family, the overlap capacitance is totally diminished. So the major factors dominating in this region, in this parasitic capacitance are the overlap capacitance and outer fringe capacitance and inner fringe capacitance. These fringe capacitance are dominated and they can be fused they can be fused, they can be fused using the various spacer dielectric, and they can also be tuned with varying with optimized underlap without mitigating the drive current capability of the device. The use of high-K spacer in the underlap double-gate MOSFET device enhances the figure of merit of the device in terms of gain and gain product. It also enhances the gate fringe induced barrier lowering strength and ultimately improve the drive current, leading to enhancement the device and circuit performance. The high-K spacer dielectric also enhances the barrier height, which reduces the off current, suppress the short channel effect in terms of subthreshold flow and behavior draining the barrier. Some researchers introduce the dual phase spacer, which is an alternative in the spacer region for a high K gate dielectric device to further limit the short channel effect and reduce the output conductance of the device. It improves the analog performance of the device and it is used for the low power circuit application. Symmetric dual case spacer means that the both sides of the source and drain are have a equal underlap length and they are the dual K has the outer K as a low K spacer and the inner K gate dielectric inner K spacer dielectric is a high K gate spacer dielectric. The symmetric dual K spacer dielectric enhances the electrostatic integrity over the channel region with the both on and off state, which ultimately reduces the device and circuit performance. Enhanced noise margin and circuit delay can also be achieved using the dual K spacer based logic circuits and ultimately make it permanent for high K spacer materials. In triangle FinFET devices, source side dual K spacer has a good grip control on the channel charge carrier, which ultimately affects the transconductance and output conductance of the device, leading to the enhancement of the analog and RF figure of merit in terms of intrinsic gain, unity cutoff frequency, unity power gain frequency, and gain side shift. For a constant of current level, the dual spacer in junctionless transistor enhances the performance of the device in terms of DIDL, subthreshold flow, on current when compared with the conventional junctionless transistor. These methods are reported by the many of the researchers reported in various peer-reviewed journals. So, if we reduce the dielectric constant in the underlap region, we mitigate the parasitic capacitance in terms of the outer fringe capacitance. So Conventionally, the least dielectric is the silicon dioxide, which has a dielectric constant of the 3.9, relative dielectric constant of 3.9. But if we use vacuum or air as a spacer dielectric in the underlap region, then this reduction in the parasitic capacitance also includes. So this leads to the result of for improving the airspace technology. The use of the low-case space under region reduces the fringing speed of the design, resulting in the improvement in the fringe depth. This reduces the short channel flux and power consumption, ultimately enhances the uh, s- speed, switching charges, switching energy, and reduce the power dissipation. Hence, as we know that the use of low-case spacer reduces the parasitic capacitance, leading to the reduction in overall device capacitance. Hence, the delay of the device is improved. Gate side air gap structure in MOSFET device reduces the fringe capacitance, which result in low power dissipation and high speed of the operation. Use of air spacer instead of the conventional silicon dioxide and silicon nitride spacer. Electrostatic integrity and the performance of the device enhanced for a fixed value of the equivalent oxide thickness and the output. Since air has already discussed that air has this dielectric constant called 1. Its parasitic capacitance is minimized with the use of air spacer as a spacer dielectric in the there there are the fabrication process. These are the fabrication process of the bulk FinFET with enhanced gap structure. The fabrication is carried by the Channing group headed by the Dr. SHIKAR, and the fabrication takes place at the National Center for High Performance Computing, Chin City, Taiwan. The fabrication as follows that firstly the bulk FinFET of silicon wafer is doped with a concentration of 10 power per 17 per centimeter cube. The fin width of about 15 nanometer were defined using a resist trimming and reoxidation and etched using reactive ion etching to a depth of 120 nanometer, followed with filling and each bag of shallow trench isolation using high density plasma chemical vapor deposition. The final fin width above shallow trench isolation was about 35 nanometer. The punch through stopper and the P-well implant were performed in two steps. The first one is the BF2 was implemented at an energy of 45 kilo electron volt with a dose rate of 5 into 10 power 13 per centimeter square with a tilt angle of 7 degree. Secondly, boron was implanted at a energy of 15 kilo electron volt dose at a dose rate of 10 to the power 13 per centimeter dose at a tilt angle of 7 degree. The punch-through stopper implements conditions are chosen to minimize the sub-channel conduction in bulk. 2.9 nanometer of hafnium dioxide were deposited as a gate oxide using atomic layer deposition. 50 nanometer of titanium nitrate was deposited as a gate metal using physical vapor deposition. The gate stack was etched using a reactive ion etching, which result in a figure 4a. This the whole process up to now is represented in 4a. Now, the bulk FinFET was formed after etching of the gate stack and implantation of lightly doped source drain region as shown in figure 4a. This is the figure 4a. To form an Encased air gap structure, carbon was selectively deposited on the side wall of the gate stack using focused ion beam, as shown in the figure 2. Here, the focused ion beam, that carbon, that purple color represent the carbon, that it is selectively deposited over the underlap region, and once it is deposited, the silicon nitride is then deposited and reactive ion RIE, reactive ion etching was performed. This result into the encased silicon nitride. Oh, this is the encased silicon nitride over the region, and finally the silicon nitride is etched in the spacer region away from the active device to create an opening. So the silicon nitride is etched. This is the active region as it is discussed, as it's shown in the figure 40. The device was then, after the selectively deposition of the silicon nitride, the carbon followed by the silicon nitride deposition, the device was exposed to the mild oxygen plasma. This process is similar to the etching process, which is known to remove the carbon. The byproduct of this process escapes through the opening in the spacer region. Resulting spacer structure consists of an air gap encased between the silicon nitride layer and the side wall of the gate stack. To form the highly doped source drain region, the arsenic was implanted at an energy of 8 kilo-electron volt with a dose rate of 5 into 10 power 15 per centimeter square and a tilt angle of 0. The dopant activation was carried out for both the silicon nitride spacer and air gap spacer device by rapid fire annealing at a 950 degrees Celsius for 5 seconds. So the final product we have formed is this. This is the TEM image of the bulk FinFET. The 5A shows the cross-sectional transmission electron microscopy image of bulk FinFET with after high K metal gate stack formation. The second figure shows that the cross-sectional scanning electron image of device after the silicon nitride spacer. Then the C shows the selective deposition of the carbon. D shows the encapsulation of the silicon nitride, and finally E shows the top view of the device showing the spacer. So these processes are used for the fabrication of the air spacer in the FinFET family. Then, what is the effect of the air spacer on the tri-gate FinFET? One of the promising effects are to reduce the parasitic capacitance, which leading to the improvement in the improvement in the RF and analog figure of merit of the device. These are discussed as now with the variation of the gate oxide thickness. As the gate oxide thickness, the equivalent gate oxide thickness is varied from the 3 nanometer to 0.65 nanometer. The conduction band energy, which is represented in the figure 7, there is a slightly deviation in the conduction band energy at lower EUT. If we use air as a spacer dielectric instead of the conventional silicon nitride spacer, there is a slightly deviation in the conduction band energy. Rather than there is a significant deviation in the conduction band energy at higher EUT of 3 nanometer. This deviation in conduction band energy can further be explained using the TEF, transconductance generation efficiency factor. As it is shown in figure 8, that at lower EUT there is a marginal shift in the transconductance generation efficiency factor at when we change the spacer dielectric from air spacer to silicon nitride spacer. However, there is a significant deviation in the TEF when silicon nitride spacer is replaced by the air spacer. This leads to the hence at lower EOT, the threshold voltage of the device won't affect, or we can say that won't change if we use air as a spacer dielectric instead of the silicon nitride dielectric. This loop, since the threshold voltage is remain constant, but we are using the air as a spacer dielectric. So there is a reduction in the capacitance. This reduction in capacitance is, we can see in figure 9c, there is a reduction in capacitance if we use air as a spacer dielectric instead of the conventional silicon nitride dielectric. Also, the transconductance gain and the output transconductance and the output conductance of the device, there is a change in transconductance or output conductance, but the output conductance is the the transconductance of the device is dominated over that output conductance. Hence, there is a marginal reduction, marginal change in the gain of the device, as we can see in figure 9c. There is a marginal reduction in the gain of the device if we use air as a spacer dielectric. But if we look at the cutoff frequency of the device, there is a huge improvement of the unity gain frequency, or we can say that the cutoff frequency. If we use air as a spacer dielectric for all the variation of the equivalent of set thickness, the cutoff frequency of the device is enhances. This lead to the further enhancement of the other figure of merit, the RF figure of merit, in terms of unity power gain frequency, transconductance frequency product, gain frequency product, and gain and transconductance frequency product. Use of air as a spacer dielectric enhances these figure of merits, and also this figure of merit enhances with the if we scale down the equivalent offset thickness. So up to now, if there is any question, I move to the next section. Anyone? Okay, thank you. So the variation with the underlap length. If we vary the underlap length, or if we can say that this is the optimization of the underlap length. So we take the two underlap length structure, 2 3 underlap structure varied from 10 nanometer to 20 nanometer device, 20 nanometer underlap device, and it is, and observe that at 20 nanometer, there is at 20 nanometer and at 10 nanometer with a fixed EOT of 0.65 nanometer, there is no such improvement in the conduction gain energy and transconduction generation efficiency factor. So there is not as such a significant change in the transconductance and the output conductance. But since we are using the air as a spacer dielectric, and we are optimizing the underlap length, uh, there is a improvement in the capacitance of the device. So if we reduce the underlap length, the capacitance of the devices increases, as we can see in the figure 13b. The intrinsic capacitance and the drain to gate capacitance of the device increase if we reduce the underlap length from 20 nanometer to 10 nanometer. So this increase in the capacitance leading to the reduction in the cutoff frequency of the device when we optimize the length from 20 nanometer to 10 nanometer. And this is also observed in the other figure of merit of the device like Fmax, TFP, GFP, and GTFP for a fixed EOT. So it is observed that if we optimize the underlap length to 20 nanometer and fix the EOT at 0.65 nanometer, then we can use air as a spacer dielectric for a low power, high frequency application, and it can be used for the low power circuit application also. Now, what is the effect of air spacer in the tunnel fat? As we know that a tunnel fat is a PIN junction diode, and if we introduce the underlap in the tunnel fat, there is a reduction in the capacitance, as we already discussed. If we use dual case spacer in this underlap region, there is a effect of both high K and low K spacer dielectric. So basically, what we have done, we have used a dual K spacer in the underlap region using inner K as a high K spacer material of HFO2 and lower K as and outer K as a low K spacer material. And we analyzed what is the effect on this. So one of the promising fact in the tunnel FET is its tunneling length, that you can see that the left side of figure 16, there is an energy band diagram. There is a band bending, and this band bending shows the tunneling length. Tunneling length is the L2 minus L1. So if we use a single spacer of high K silicon nitride, then aluminum uh, HFO2, dual K spacer, and AI spacer, then the tunneling length is significantly reduces. If we use a high K spacer, if we use dual K spacer instead of high K spacer like HFO2, the tunneling length is further reduced. And if we use uh, air as a outer low K spacer dielectric in the underlap region of the dual K tunnel FET, this tunneling length is further reduced. The tunneling length is the one of the promising factor for deciding the current in the tunnel FET, because the tunneling length affect the band-to-band generation factor, which ultimately enhances the average electric field in the tunneling region, and which ultimately lead to the drive current of the device. So if we reduce the tunneling length, we enhances the band-to-band generation factor and enhances the average electric field in the tunneling region, and which ultimately increases the drive current of the device, as it is shown in the figure 18. That use of dual K spacer increases the drive current of the device instead of using the high K spacer. And if we use air as a outer K spacer dielectric in the tunneling region, in the underlap region, then this enhancement in the drive current is also improved. Further, the subthreshold slope of the dual K spacer device is reduces, which is very good in TFET, and this reduction is also observed in air as a outer K spacer dielectric in the tunnel device. Finally, the other figure of merits like transconductance, output conductance, and device capacitances also improve when we use dual K spacer dielectric in the tunneling in the underlap region of the tunnel FET, and this leads to the enhancement in the intrinsic gain and cutoff frequency of the device when we use dual K spacer, and this is further improved when we use air as a outer spacer dielectric in the tunneling region. The other figure of merits like unity power gain frequency, transconductor frequency product, gain frequency product, and gain transconductor frequency product, the results are mm, pretty much good, that use of air as a outer low K spacer dielectric in the dual K spacer under left hand FET enhances these performances. The next device we are going to discuss is the silicon nanowire, and you can simply, in simple way, we can call it a gate all around MOSFET, gate all around silicon nanowire. There are many silicon nanowire. There are silicon nanofets. There are many names by many researchers. So this is a silicon nanowire structure, and in the underlap, this is the underlap region. We are observing the here we are also observing the effect of air spacer in the underlap region of silicon nanowire, or cylindrical, or gate all around silicon nanowire, whatever you are willing to say, you can say that on gate all around silicon nanowire FETs. It is observed that for the device is simulated at a diameter of nanowire of 10 nanometer, and we have varied the equivalent oxide thickness from 0.6 nanometer to 1.2 nanometer, and we have also varied the underlap length from 8 nanometer to 12 nanometer. The gate length of the device is around 12 nanometer. So figure 25 shows that there is a slightly deviation in the conduction band energy if we use air as a spacer dielectric in the underlap region. However, there is a huge deviation in the conduction band energy at higher EOT if we use air as a spacer dielectric in the conduction band and conduction uh, in the conduction band energy. This result replicates the transconductor generation efficiency, and it is observed that there is a slightly deviation in the air between the air spacer and nitrile spacer at lower EOT, and a significant deviation between the air spacer and nitrile spacer at higher EOT. This leads to that at lower EOT there is no change in the threshold voltage of the device, which ultimately enhances the transconductance and output conductance of the device for air spacer device. Figure 27a shows that the transconductance output conductance variation with the equivalent oxide thickness. If we scale down the EOT from 1.2 nanometer to 0.6 nanometer, there is a reduction in the transconductance, and there is also reduction in the output conductance, but this reduction is our transconductance is dominated over the reduction in output conductance. So there is a improvement in the intrinsic gain when we scale down the EOT from 0.6 from the 1.2 to 0.6. Also, as we know that we are using the air spacer instead of the conventional silicon dioxide and silicon nitride spacer. There is a reduction in the capacitance of the device, leading to the enhancement in the cutoff frequency of the device. This improvement also replicate in the other figure of merit of the device like Fmax, PFE, GFE, and GTE. The result we have extracted for all the in all the device is at 10 microampere per micrometer. We are taking this point as a weak inversion or moderate inversion point for the extraction. Variation with the underlap, as we varied the underlap length from 12 nanometer to 8 nanometer. There is a there is not a such a significant, but in 12 nanometer underlap length, the deviation in the conduction band energy between the air spacer and the nitrile spacer is quite small rather than the deviation in conduction band energy between the air spacer and nitrile spacer at 8 nanometer underlap length. Hence, if we scale the length, the output conductance of the device increases, which is not beneficiary for the device, and this lead to the reduction in the intrinsic gain of the device. Also, the capacitance of the device increases, which leads to the reduction in the cutoff frequency of the device if we scale or we can say that if we optimize the underlap length from 12 nanometer to 8 nanometer. So it is concluded that if we use 12 nanometer underlap length with a equivalent oxide thickness of 0.6 nanometer and a struggle length of 1 nanometer, the gate all-around silicon nanowire MOSFET is can be best used as a a spacer MOSFET for high performance and low power application. If we vary the temperature, the operating temperature, suppose we have to use a MOSFET or a MOSFET device at a cryogenic level, at a liquid temperature level, or in the space application. So we have to check the at which temperature range the device will work in a good manner. So if we lower down the temperature, there is a significant reduction in the conduction band energy, and this is also replicated in the transconduction generation efficiency, that at low temperature the transconductance generation, there is huge improvement in the transconductance generation efficiency, leading to the improvement in the transconductance and the output conductance. But the increase in the transconductance dominates over the increase in the output conductance. Hence, the gain of the device increases when we reduce the operating temperature from 400 Kelvin to 100 Kelvin. Also, it is observed that there is not a such deviation in the capacitance of the device when we varied the operating temperature from 400 Kelvin to 100 Kelvin. But since there is a improvement in the transconductance of the device, so there is a improvement in the cutoff frequency of the device. Since because the cutoff frequency is the ratio of the transconductance and the intrinsic capacitance of the device. Yes? The cutoff frequency or unity current gain frequency increases when we lower the temperature from 400 Kelvin to 100 Kelvin. Since there is an improvement in the gain and the transconductance and the cutoff frequency, hence there is a improvement in the other RF figure of merit like maximum oscillation gain frequency, transconductance frequency product, gain transconductance frequency product, and gain frequency product. Up to now, is there is any question? Please let me know. Because we are going to discuss the circuit application part of the AI spacer based MOS devices. So if there is any query up to now, please let me know. So shall I proceed further now? Okay, I'm
Yeah,
proceeding here
I
further.
believe no query is there, so I can
Hmm.
request Dr. Shikar to move to the circuit.
Okay, thank you. Thank you, Dr. Tyal. So, as up to now, we have discussed that air in the underlap region, or we can say that the air spacer in the underlap region is the one of the most promising candidate for reducing the intrinsic capacitances or improving the intrinsic capacitance of the device. And if we optimize the underlap length and the equivalent oxide thickness, and further we can optimize the straggle length and the silicon film thickness. We can use air as a special dielectric material and use that device as a circuit application. So I'm presenting a work. I'm presenting the use of air as a special dielectric based MOSFET on the performance of operational transconductance amplifier. Operational transconductance amplifier is a type of op-amp. You can say that it is a type of op-amp where a current mirror is connected to the so these are the circuitry of the op-amp. So it is observed from the various analysis over the TCAD, and there are various methods we can use these devices which we modeled in the TCAD. That one of the use is the mixed mode simulation in the TCAD itself. Another use of we can use the BSIM CMG model, BSIM CMG model which is available online, and we can tune the parameters over there according to our benefits, according to our device, and model that BSIM CMG model and use that BSIM CMG in the any circuit simulator like Cadence Virtuoso. Thirdly, there is a Verilog A model method in which we have used that various IDVG and CV curves for analyzing for various gate and drain voltage, and use that Verilog code in the circuit to observe the performance of the device on the circuit and application. So, what based on that, we have analyzed that if we use air as a special dielectric in the underlap region instead of conventional silicon nitride special dielectric, the gain of the device increases, as we can see in figure 37 on the left hand side, that the gain of the device increases. Also, since the gain of the device increases, so there is a increase in the CMRR, common mode rejection ratio of the device. It is observed that at 3 nanometer EOT for air specialist device, the gain is observed at 146 gigahertz, while for silicon nitride device, it is observed at 80.72 gigahertz at lower EOT of 0.6. The gain is observed at 156 gigahertz, and for the air silicon nitride spacer device, the gain is observed the for 104 gigahertz. The cutoff frequency is significantly improved when we use the AF spacer for the circuit application. Also, if we value the underlapping and how we optimize the underlapping from 20 nanometer to 10 nanometer, there is also an improvement in the cutoff frequency. As we see the left hand side of the figure 38, there is an improvement in the cutoff frequency. From figure 38 on the left hand side, which shows the gain versus frequency, the unity gain frequency observed for 20 nanometer semiconductor-based device is 156.72 GHz for a silicon nitride spacer device. However, for underlap length of 10 nanometer, cutoff frequency is observed for 140 GHz for air spacer and 74 GHz for nitride space. So we can it is observed there is a huge deviation, huge improvement in the cutoff frequency of the circuit, unity gain frequency, and in circuit application it is called as unity gain frequency. So it is a huge improvement in the unity gain frequency of the circuit if we use air as a spacer dielectric. And it is also observed that the CMRR is also enhanced. So I am concluding with the fact that air as a outer spacer dielectric or a spacer dielectric in the underlap region of any MOS family device can lead to enhancement in the, or we can say that reduction in the parasitic capacitance, enhancement in the capacitance, which lead to the enhancement in the cutoff frequency or unity current gain frequency, unity power gain frequency, and other RF figure of merits. This lead make it suitable for low power, high frequency application. Okay, thank you. Any queries from the audience?
If there is any query from the participants, please feel free to ask Dr. Shikhar. Please unmute yourself and you can ask. Thank you.
Hello, Dr. Gupta.
Hello.
Hello. Yeah, it was a very good presentation. I have two questions.
Yes, sir.
The first one is your simulation results and experimental results, are they matching? If so,
Yeah.
you usually when we make a device, we encounter with many sort of contaminations. And I
Mm-hmm.
know during the simulations there is no specific parameters to introduce this kind of a disorder other than interface
Mm-hmm.
defects.
Mm-hmm.
So during the simulations, did you take the effect of those irregularities? Because in the software you define a perfect square, but when you actually measure, it will not be a
Mm-hmm.
square, it would be rounded edges. Because
Yeah,
you are
yeah.
working on nano scale,
Yeah, yeah.
even if you're off by 10% or 20%, it will
Mm-hmm.
make a big difference. So I just
Mm-hmm.
wonder if you
Mm-hmm.
have taken that into consideration during simulations.
So for that thing, we have modeled our TCAD. We have taken some experimental data for that for gate all-around silicon nanowire. I have used the experimental data from TSMC. It is reported in a paper. Uh, Unfortunately, I didn't recognize that paper, but the device is fabricated in the TSMC, and for the 10 nanometer diameter of silicon nanowire, and they have reported the experimental result. So I have taken that experimental result and calibrated the ticket setup. So
Oh,
calibration of the ticket setup will consider all the effects, all the other effects, all the X factor, while we are not considering, mm, while we are generally not considered during the ticket simulation. So first we have calibrated, and one of in our research group, the FinFET is also calibrated by Dr. Nandi, and we have taken that FinFET model for the calibration of the FinFET devices.
okay. So if I understand it right, so what you're saying is you have a device model, you
Mm-hmm.
have an experimental result. So you
Yeah.
will use the device model to match the experimental results and calibrate your model so that it is mimicking the
Yeah.
reported experimental value.
Yeah, exactly.
So you do pre-calibration before doing the simulations.
Yeah,
Is
yeah.
that right,
Before doing
Dr.
that,
Gupta?
we have to pre-calibration.
Oh, okay. Thank you. Thank you for the clarification.
Okay, sir.
Oh, okay. And one last question
Yes,
on
sir.
figure number 38. Uh,
Yes.
Using the eight spacer technology, the gain is increased, but I do see a two slope phenomenon during the roll off in figure 38. Usually the gain is constant, and then I see two slopes, not one slope in the roll off region. I hope you got it on figure
Yeah,
38.
yeah. So figure 38 replicates the, let me show again.
Yes, exactly this one. Or if you look at the right side one or the left side one,
Yes, sir.
after the gain region, right around 10 to the power of 10 and 10 to the power of 9, I
Yeah,
see
yeah.
two slopes in the roll off region.
Yeah, yeah.
So I
So,
just wonder, could you please comment on why I'm getting two slopes in the roll off region?
in the, sir, it is in if in the op-amp, if there is a cutoff frequency, after that the gain is reduced.
Yes, yes.
So this roll-off region is due to because of that.
Yeah, I understand that, but it usually you have one cutoff frequency, so you should get one slope. But
So
I
we
just
we
want,
have four devices, sir. Here we have four devices. We have device for two underlap length, and for
okay,
both the underlap length, we have used the air spacer device and silicon nitride spacer device. So conventionally, we have two devices. So we have we have four devices, and so that we have four roll-offs.
okay. Thank you, Dr. Gupta, for your detailed explanation. Thanks a lot.
Okay, sir.
Any other queries from the participants? Or can we wind up the session? If can I assume it that there is no query?
If someone has a query, you can mail me. You can mail me or shikhar.gupta2@gmail.com. I will write my email ID over the chat box. If you have any type of query, you can mail me. Free to mail me. I I will happy to answer all of your queries.
So I believe there is no much queries pending.
Hmm.
So on behalf of SR University, I want to would like to thank Dr. Shikhar for such a thoughtful interaction on the topic spacer technology in multi-gate devices, and looking forward to have you in further sessions or future FDPs, Dr. Shikhar, and really thankful to accept our invitation in such short span of time. Very thankful to you, Dr. Shikhar.
Thank you, Dr. Dayal.
And I would like to thank participants also to be being there from the morning till afternoon. Today's session, then we are winding up today's session. Again, we will meet tomorrow in the morning session, sharp 10 o'clock. And tomorrow we will be having Dr. R. Shashank and Dr. Sandeep Bhattacharya, who will be talking about interconnects and their role in low power VLSI. And the evening session will be there by Dr. Shweta Meena on magnetic tunnel junctions, that which different kind of 2D materials we can have for magnetic tunnel junction.
I request all the participants to give the feedback. If link is open, please give the feedback link. Some participants are already posted their feedback, but carefully post the speaker name, since the speaker name is mandatory for the session. Session means if particular speaker name is matching means then only we will take. Otherwise it will be discarded. So please keep take care of the speaker's name. Thank you. We will meet.